Have you ever felt like there's a secret language hidden inside the math formulas we all had to memorize? Well, today, we're pulling back the curtain on one of the biggest secrets in statistics. It's hiding in plain sight, in a formula you've probably seen 100 times. And once you see it, it's going to completely change how you think about statistical inference.
Ah, yes, this old friend. If you've taken even one stats class, you know this formula for the z-statistic. It's everywhere, right? We use it for hypothesis tests, for confidence intervals, we just plug and chug. But have you ever really stopped and looked at it? I mean, really looked at it, because there's something weird going on here.
And here it is. This is the paradox. Think about it. We're taught that a statistic is something you calculate only from your sample data. Your sample mean, your sample standard deviation, all stuff you know. It can't have any unknown population values in it. But, look, right there, smack in the middle, is mu, the true population mean, the very thing we almost never know. So, what's the deal? How can we call this a statistic?
To solve this little mystery, we need to understand that this formula is actually a bit of a chameleon. It's not one thing. It's playing two totally different parts depending on the situation. It looks like one concept, but it's really two.
Yep. The entire secret boils down to the difference between two things that look like twins, something called a pivotal quantity and its much more famous sibling, the test statistic. They look the same, they feel the same, but trust me, they have fundamentally different jobs.
So, let's start with the unsung hero, the one working behind the scenes that you might not have even heard of. Let's talk about the pivotal quantity.
Okay, so a pivotal quantity is a really special kind of formula. It's this clever mix of stuff we have, our sample data, and the one thing we don't have, that unknown parameter. But here's the absolute magic trick. Even with that unknown value floating around in there, we somehow know its exact probability distribution. Whether it's a standard normal or a t-distribution, we know its shape, and that shape doesn't change no matter what the unknown parameter is. It's amazing. So really, it all comes down to two simple rules. Rule 1, it's got to have both sample data and an unknown parameter in the mix. And rule 2, despite that unknown, we know its distribution perfectly. That second rule is its superpower. That's what makes it so incredibly useful.
All right, now for the one we all recognize, the famous test statistic. So how is this different from what we just talked about? Let's take a look. Now, let's get really strict for a second. A true blue statistic has one simple rule. You can only use your sample data to calculate it. That's it. You take your sample, you crunch the numbers you have, and you get a value. No unknowns, no what-ifs, and absolutely no mysterious Greek letters for population values allowed. Period.
So when you put them side by side, boom, it just clicks. The only thing, the single tiny difference between a pivotal quantity and a test statistic is that unknown parameter. One has it and one doesn't. So, how do we get rid of it? How do we go from one to the other?
And here we go. This is the moment the magic happens. This is the simple, almost deceptively simple step that turns our mysterious pivotal quantity into a hardworking test statistic.
Check this out. It's just a few logical steps. We start with our pivotal quantity, with that unknown mu hanging out in there. Then, when we do a hypothesis test, what do? We state a null hypothesis. We basically say, hey, what if mu is equal to a specific number, like 10? Step 3, we just plug that number in for mu. And just like that, poof, the unknown is gone. What we have left is a formula with just our sample data and some numbers. It is now officially a test statistic. We can actually calculate it.
This really hits the nail on the head. The moment you specify a value for that parameter, the moment you make a hypothesis, your pivotal quantity transforms into a test statistic. It's not a new formula, it's the same formula, just playing a different role in the game.
Okay, so that's a pretty neat trick, right? But so what? Why do we even need these two different ideas? Well, it's because they are built for the two biggest jobs in all of statistical inference.
Seriously, this isn't just some fun fact for a stats trivia night. This distinction is the bedrock that hypothesis testing and confidence intervals are built on. They're like two sides of the same coin, and you could say the pivotal quantity is the coin itself.
This table just lays it all out perfectly. On one hand, you've got the pivotal quantity. Its whole purpose is for building confidence intervals. You keep the parameter as an unknown variable so you can build an equation around it and solve for a range of plausible values. But on the other hand, you have the test statistic. Its job is hypothesis testing, making a decision. You get rid of the unknown by plugging in a specific value from your null hypothesis. This lets you calculate one single number that helps you decide, do we reject the null or not? Two tools, two totally different jobs, all from the same starting point.
So the next time you see that Z formula, you'll know its secret. You'll know it's not just one thing. It's a pivotal quantity when you need a range, and it's a test statistic when you need a decision. And it kind of makes you wonder, doesn't it? What other rules that we all just take for granted are actually these beautiful, elegant transformations just waiting for us to notice?